Greetings, my name is Arianna Colón Cesaní, and today I'll be talking about my MIT Summer Research Program project, where I'll be discussing the interactions between PeV cosmic rays and local galactic molecular clouds can explain the positron excess near Earth. So cosmic rays are energetic particles that are traveling through the galaxy at very high velocities, and they can serve as messengers of astrophysical phenomena in the Milky Way and beyond. We know that they're made up of protons and alpha particles for the most part, and they're not harmful to us at Earth's surface because the atmosphere is protecting us. And the main subatomic particle that I'm going to be discussing in this work is the positron. Positrons are positively charged electron counterparts that are produced in proton-proton interactions as secondary products. And not only are these rare in the galaxy, but we know that the positron rate should decrease with energy due to the losses in the collisions of the cosmic rays as they're traveling through the Milky Way. But this isn't what's been observed so far with the positrons. So as you can see in figure 1, which is shown here to the right, the positron excess is shown as a function of energy, and the rate is increasing with energy instead of decreasing as is expected. So we know that a high energy source must exist in order to explain this behavior. And we know that it contributes somewhere between 1 to 10 GeV per inverse meter squared per second per steradian at Earth. And electrons, as well as positrons, lose energy within short distances of around 3,000 light years. So we know that this source must also be close to the solar system. And many possible explanations have been proposed to try to explain this excess, but there isn't enough data to show definitively that these are the real reason behind the positron excess. So some of these include dark matter particle processes, shocks from pulsar wind nebula, and the reacceleration of positrons in nearby molecular clouds. But our project proposes a mechanism in which PeV cosmic rays interact with nearby molecular clouds, which are within 3,000 light years of the solar system. And then in the interactions of the cosmic ray protons with the protons in the clouds, positrons of 1,000th of these energies are produced and then travel to Earth where we can detect the excess. So we use new lists and catalogs of molecular clouds and selected 10, which have been shown here to the right in table 1. And we considered the interactions with these clouds that are within 3,000 light years of the solar system and have masses between 1,000 and 100,000 solar masses. And PeV protons have been detected directly at Earth, and we're specifically interested in them because they haven't been included thus far in the same models that are having difficulties explaining the positron excess. And in the next couple of slides, I'll be talking about the estimate of the total PeV proton rate in the galaxy. And when I mentioned that, I'm referring to the ith-top all-particle cosmic ray flux, which we estimated by multiplying the average energy per bin in their data by the corresponding flux and then adding up all of the values. And so we considered a simplified model, which assumed that PeV protons were traveling in straight lines towards these spherical clouds of uniform density. And then in the interactions inside of the clouds, TeV positrons can be produced and then travel to Earth where we can detect the excess. And so we started off with the PeV cosmic ray proton rate in the galaxy, and we proceeded to calculate the energy of these proton-proton interactions produced per second. So to do this, we estimated the center of mass energy for PeV proton and galactic molecular cloud collisions, the cross-section of these proton-proton interactions at high energies, the density of the clouds, assuming they were uniform spheres, and the average distance traveled by the protons inside of the clouds when they were interacting. And the interaction cross-section we actually got from the particle data group tables. And then we proceeded to assume that 1/3 of this energy is used to produce the positrons. And using diffusion and energy spectrum formulas from previous work, we were able to determine the individual upper limits of the positron rates being produced in each molecular cloud that was reaching us at Earth. And then using these 10 individual values, we added them up and then got our total rate of positrons at Earth from all of these clouds. And so in conclusion, our proposed mechanism is not a reasonable candidate to explain the axis. And this is because our result is about 3 orders of magnitude smaller than the total AMS positron rate, which I previously mentioned. So future work could consider maybe the PeV proton implications or effects on other particle spectrums. And we could focus on trying to come up with new ideas to try to explain this positron excess. But in conclusion, the contributions of PeV protons and their interactions with nearby molecular clouds isn't enough to explain the positron excess that's detected in our solar system. Thank you very much, and I hope you have a great day.